Hello everyone, I'm Olive Surin from ECE Section B, and today I'm here to discuss about the two different types of bipolar junction transistors, which are the NPN type and the PNP type. Transistors. Transistors are categorized into two types, BJT and FET. BJT is further divided into two types, type transistors and PNP type transistors. NPN type transistors. NPN type transistors are a type of bipolar junction transistors composed of two layers of N type semiconductor material with a layer of P type material in between. These are composed of three layers of regions. First, the emitter region. Second, the middle region is the base region, and another side of this transistor is the collector region, where the emitter region is on one side, which is highly doped, and in between is the base region, which is lightly doped, and the collector region is moderately doped. The doped. This is the symbol uh, of an NPN transistor, in which the arrow depicts the direction of current. Working of an NPN transistor. uh, First, the NP junction in an NPN transistor is forward biased, and the PN side is reverse biased, in which when an electric voltage is applied in the N side and a positive voltage is connected to the P side is applied, it pushes the holes in the P region towards the base region. Meanwhile, free electrons in the base region gets attracted towards the positive and move towards emitter, and holes move to the base region. And as base region is lightly doped and emitter being highly doped, so only a little amount of electrons and holes combine, while the rest of the holes move towards the collector region. Thus, due to the motion of holes from emitter to the collector, we get some current, that is the IE current. Also, how when the holes move to the collector region, as this junction is reverse biased, negative terminal attract the holes towards itself. A huge amount of current flows in collector region, thus due to which an IC current is obtained and an IB current is also obtained. Due to the Kirchhoff's rule, IE is also equals to IB plus IC. For the working of NPN transistor, as we know, this part of the transistor is forward biased and this part of the transistor is reverse biased. So, when a small voltage is in the forward bias direction is applied, the depletion region is thin in the forward bias. The electrons, the majority carrier of the N type, repel and move towards the P region, and similarly holes, the majority carriers of P type region, move towards the N type. Electrons move and combine with holes in the base, and as base is lightly doped and emitter is highly doped, some electrons combine with the holes and the rest of the electrons move towards the collector region. As we know that the direction of charge is opposite to the direction of current, therefore due to the motion of electrons from emitter region to the collector region, and a current is generated, that is IE, in the opposite direction. As we know, in the P region, the combined electrons move to the valence shell, due to which the positive charges move to the base region. So we get an IB current. Also, due to the movement of charge from emitter to the collector, we get an IC current in the opposite direction. So, by the Kirchhoff's rule, we get an equation that IE is equals to IB plus IC. The NPN device also operates in three regions: active region, cutoff region, and saturation region, in which in which the active region in the active region the base emitter is forward biased and the base collector is reverse biased. In cutoff region, base emitter is reverse biased and the base collector is reverse biased. Also, in the saturation region, both the base emitter and the base collector are forward biased.
Hello everyone, I am Siddhi Dwivedi from ECE section B, and today I am going to discuss about transistor configurations, the three different types of transistor configurations. Okay, so we will dive into the three fundamental transistor configurations: common base, common emitter, and common collector. We will explore the unique characteristics and visualize their input and output characteristics on graph. Starting with common base configuration, the input signal here is applied to the emitter, output is taken from the collector, and base is common to both the input and output. Coming to the input characteristics, there is a plot between IE, this emitter current, and emitter base voltage VBE. There's an exponential rise in IE with respect to VBE. With VCB constant, gives a constant graph. Moving on to the output characteristics, there's a plot between IC and your VCB, your collector base voltage. With constant value of IE, we get constant graphs. This region, when IE is 0, the region below that is known as the cutoff region. This region is known as the active region, and this region is known as the saturation region. Cutoff, saturation, and active region. Okay, now moving on to common emitter configuration. Here the input signal is applied to the base and the output is taken from the collector, and your emitter is common to both input and output. Moving to the input characteristics, the plot between IB versus VBE, and it will be constant for a constant value of VCE, and shows an exponential rise in IB with respect to VBE. Now moving on to the output characteristics, there's a plot between IC and VCE, and the graph is constant for constant value of IB. Here again, this would be your saturation region, active region, and when IB is almost 0, region below that is cutoff region. Saturation and active region. Now coming to the last configuration, which is your common collector configuration. Here the input signal is applied to the base, output is taken from the emitter, and collector is common to both input and output. Now the input characteristics for common collector has a plot between IB, which is your base current, and VBC. The graph goes linear and it decreases with respect to increase in VBC for a constant value of VCE. Now output characteristics are similar for all the three transistor configurations, with the plot between IE and VCE. right? And it is constant for constant values if IB. Again, saturation, active, and cut off. So yes, that is all, and yeah, thank you.
Hello everyone, I'm Qamareen Fatima from ECE Section A, and today I'm going to discuss fixed biasing and voltage divider biasing in BJTs. So let's begin. So first of all, we have fixed biasing. What is fixed biasing? Fixed biasing is a simple method where a resistor called the base resistor is applied across the source voltage and the base of the transistor, and this sets up a constant base current IB in the circuit, and the current IB in turn fixes the collector current IC. And in this configuration we can see that this is the equivalent circuit, and here we have the source voltage VCC and the current IB, the resistance RB, and the base collector emitter. The emitter is grounded, and we have a resistance across the collector as well. If we try to redraw this circuit, it's going to look something like this. Here, the base emitter junction is in forward bias condition, and the transistor operates in active region. And this voltage is called VBE, and this voltage is called VCE. We can see that VBE is on the input side of the circuit, and VCE is on the output side of the circuit. If we try to write KCL in the two loops, for loop 1 we'll get VCC minus IB RB minus VBE is equal to 0. Then VCC minus VBE upon RB is going to be IB, which is the base current. Now we can plot this input characteristic curve using this value of IB and the input voltage VBE for various values of VCC, and this is our this graph represents our input characteristic. And when we try to write KCL in the second loop, it's going to be VCC minus ICRC minus VCE is equal to 0. So IC can be given similarly, VCC minus VCE upon RC. Now we can plot the curve between IC and VCE for various values of IB. Here IB is equal to 0, and we go on increasing the values of IB, and IC will also increase respectively, and for a similar case for VCC. Now, why do we need this fixed biasing configuration? What is the importance? So the most important advantage of using this configuration is that it is simple to design and that it requires less components. So that is why we use it. And the second thing is, when we discuss about the disadvantages of this fixed biasing configuration, it is that it is very sensitive. To temperature changes. And when it is sensitive to temperature changes, the Q point for the circuit will also shift very drastically for even a little change in temperature. So it leads to instability and shifting of operation points, and leading to clipped circuits and undesirable outputs. So that is all for fixed biasing configuration. Now we are going to discuss the other biasing, that is voltage divider biasing. Now in the second case we are going to discuss voltage divider biasing. It is sort of a solution to the problem that our fixed biasing poses. So fixed biasing is unstable because of temperature variations and it is not able to handle it. Divider biasing solves that problem, since it is a more stable biasing that uses two resistors and it supplies a stable base voltage, making it less dependent on temperature changes, and it has emitter resistor to further stabilize it. In this case we apply another resistance to the emitter and ground, between the emitter and the ground, and we have two resistance from the base, and and the equivalent circuit looks something like this. And the base emitter is in forward bias condition, and the entire circuit acts in the active region. So if we try to redraw this circuit, it looks something like this. If we complete the circuit and remove all these extra capacitance, this is our E, this is our base, this is our emitter, and this is our collector. So if we try to find out the equivalent resistance in this portion, and this is a voltage actually, the circuit diagram was a little inaccurate. Now this is the voltage. If we try to find out the equivalent voltage over this area, it's going to we are going to calculate it using Thevenin's equation. So according to that, the equivalent resistance is going to be R1 R2 divided by R1 plus R2, since R1 is parallel to R2 in this case. And when we try to find out the V Thevenin, it's going to be R2 upon R1 plus R2 into VCC. This is going to be our voltage. Now we can redraw the circuit to simplify it. It's going to look like this. We have resistance RTH and we have this voltage VTH, and then we're going to have this transistor, and then the resistance RC, this is VCC, and here we have the emitter RE, and this is gonna be grounded, or even if we don't make it, it's fine, it's understandable. And then we are going to write down the KCL equations in these two loops. First of all, this is VBE and this is VCE. It's gonna simplify our calculations when we are writing. This is loop 1, this is loop 2. Now we are going to write the equation. It's gonna be VTH minus IB RTH minus VBE minus IERE is equal to 0. So VTH minus VBE is equal to IBRTH plus IERE. And we know that there is a relation between IE and IB. It is that IE is equal to IB into beta plus 1. So we can find out the value of IB by putting this over here. VTH minus VBE upon RTH plus RE into beta plus 1 is equal to IB. This is our equation, and similarly we can write down the equation for the second loop, and it's gonna give us that VCC minus IC into RC plus RE is equal to VCE. Since we are using the assumption that IC is almost entirely equal to IE, So we are writing this, and with this we find out the value of our collector current, and then we can plot the curve which is required for finding the operating point or the Q point. And using this we can find out various parameters for the circuit. That's it. And when we try to discuss about the advantages of this biasing condition, then it's going to be that it has more stability, it is less sensitive to changes, and the operating point remains stable under temperature variations. However, the disadvantage is that it requires more components and it is slightly more complex to design as compared to fixed biasing. Thank you.
Hello everyone, this is Yash Raj from ECE Section A, and today I'm going to explain collector feedback biasing and emitter biasing configuration. So let's begin. Okay, so the emitter bias circuit looks something like this, and it is similar to the fixed bias configuration. The only difference is here it contains a resistor, and here it is directly shorted to the ground. Okay, so moving forward to the emitter bias configuration. So now let's begin with the equivalent circuit. Okay, so this is the equivalent circuit of the emitter biasing configuration. You can see that I connected the two batteries VCC and connected it to the ground, the negative terminals of them, and positive terminals of them are connected to RB and RC, which is shown by this point charge here. Okay, so from this equivalent circuit, now we can apply KVL along this loop and this loop. So first of all, let's take a look on this loop. So if we move from VCC to this direction, in this direction, we will get something like. So here we can also write IE as beta plus 1 times IB. So let's do that. Simplifying this equation, we get something like. So finally we get the value of IB something like this. After simplifying the first loop of the emitter bias configuration, now let's find out the value of VCE by using this loop, applying KVL on this loop. So let's do that. Okay, so we are taking an assumption here, which is IC is nearly equal to IE. So we get the final value of VCE as this from the second loop. Okay, so now we'll start with the collector feedback biasing circuit. So as you can see, the circuit looks something like this. There is VCC which is connected to RC, And then there's a feedback introduced from collector to base, and then there's the resistor in emitter side. As we compare it with the previous circuits, and you can see that there was VCC connected to both RB and RC in the previous circuit, whereas in the collector feedback circuit, there is feedback introduced in this. So now let's take a look at the equivalent circuit. So this will be the equivalent circuit for this. And now we'll see how the current will work in this. So the base current will go simply like this, and the collector current will be called from here, and the current which goes through the resistor RC will be called IC dash. We cannot call this current IC, as you can see there's a junction in here which is the feedback to the base. So we'll call this current IC dash, and in there we can see current IE coming out of here. And VCC, we connected a battery VCC here, which is in positive terminal is connected with the RC, and negative terminal is connected to the ground. Now what we'll do is we'll apply KVL along this loop and go all the way from there to here and then come back again. So we'll go across a loop like this and then calculate the value of IB. So let's do it. As we know from Kirchhoff's current law, here you can see there's IC dash current going on, and it is getting separated in the junction into IB and IC. So we can write something like IC dash is equal to IC plus IB. Now here we can see that IB is a very small value in comparison to IC dash and C. So we can directly neglect that and write something like IC is similar to IC dash. So we'll take this approximation, and also IE is nearly equal to IC. So we'll take these two approximation, and now let's simplify the equation here. We know IC is beta times IB. So finally, we get the value of IB as this from applying KVL in this loop. Now we'll apply KVL on the outer loop, which is this one, and hence find the value of VCE. this voltage. So let's do that right now. Again, applying the following approximations. IE is similar to IC and IC is similar to IC dash. We can write finally get the value of VC as this.
Hello everyone, I'm Arnav Singh from EC Section B. I would be explaining about these bias stabilization and stability factor. So, what is bias stabilization and stability factor? After setting the Q point or the operational point, we don't want it to change. And the main reason for change in it is collector current, as it is dependent upon collector current and input voltage VCE. So, the process of making the operating point independent of temperature and variation in transistor parameters is known as stabilization. Now, the question is, what causes the unstabilization? So, any change in the value of the collector current increase or decrease causes it. IC will change with the change in the amplification factor beta, as it is given that IC is equals to beta IB plus beta plus 1 ICBO. Amplification factor is constant for a given transistor, so changing transistor can cause it to change. Also, two transistor does not have the same amplification factors. Second point, that change in temperature also causes IC to shift, as ICBO is directly proportional to temperature. So as temperature increases, ICBO also increases and it increases the IC. Hmm. As we know that ICBO is caused by the minority charge carriers. So with increase in temperature, ICBO also increases. Now the next point is the stability factor. The rate of change of collector current IC with respect to the leakage current ICBO at constant input VBE and amplification factor beta is called the stability factor, which is denoted by S. S mathematically can be shown as small change in IC divided by small change in ICBO at constant beta and VBE. There are also other two expressions which denote the stability factor. First is S dash, which is the small change in IC divided by small change in VBE at constant ICBO and beta. The third term is S double dash, which is the small change in IC divided by a small change in beta at constant ICBO and VBE. Stability factors measure the stability of a circuit. So, the lower the value of S, the more stable is the circuit. Assuming two circuits, having first circuit having stability factor 10 and the other having stability factor 8, then S2, the second circuit, is more stable than the first circuit S1.